Hi, all of you. We're starting part 2 of mechanics of breathing. Let's look at that surface, because we're imagining the alveoli filling up and oxygen going across that membrane. What does that membrane look like? So this is a diagram of the respiratory membrane, and I'm telling you that it optimizes diffusion and gas exchange. So what does it look like? If this is the inside of the alveolus, right, and this is the border of the alveolus, this is where those simple cells are, that tissue, and then I'm going to have the capillary just above this with its red blood cell inside. So what do we have on that surface? The first thing that you would have here, air is filling this, the first thing you would have is surfactant. Surfactant is lining that. Then there will be the alveolar, here in purple, alveolar epithelium, 1 cell thick. Remember that. It's going to be easy for it to cross that when it comes to oxygen. And then the capillary endothelium. So essentially we have 2 cell thick here. It's 2 cells, right? If I could draw it in, a cell would make up this liner, and then there'd be another cell here. So that's the epithelium, that it would have to go into this 1 cell, cross over to the next cell, and then make it into the red blood cell. So alveolar epithelium, capillary epithelium, and then it's in the plasma. Now it's in the fluid, and then it'll get to the red blood cell. Okay, so those are those barriers that a molecule here, or an oxygen molecule, encounters as it tries to cross over. And it's going to have a concentration gradient for that, right? There's going to be a whole lot more of that oxygen here than there is on the other side, so it's going to be able to cross over, but we're going to talk a lot more about that. In the middle of the 2 in gray here, those are just basement membranes. It's the lower end of each one of those membranes. And so that's a little thickness there it has to cross to. So remember, alveolus here, capillary there. If you had to do it again, that's a diagram for you to practice on. What is it that you're crossing here? Surfactant, and then the cells here that make up the alveolus, the cells that make up the capillary, and the plasma, and the red blood cell. Okay, switching gears here, we're going to talk about spirometry, and this is a way that we measure pulmonary function. How well you are bringing air into the lungs, and how well you're exhaling that air also. So this is a diagram that shows the mechanics of how this is done, even though this is all done on a computer now. So you wouldn't be blowing into a barrel here, but it's good to visualize. So it would imagine this container filled with water and this sort of barrel inside it. And if you were to be able to push a lot of air into this, it would lift this barrel for a certain volume, depending on how forceful you were. And attached to this line, there would be a little pen, and it would be able to make diagrams depending on when you breathed in, how it increased, and when you breathed out, how it decreased. And so you'd get a reading. Well, this is all done on a computer right now. You're actually breathing also, still have this in your mouth, and you have a nose clip, and this in your mouth, and you would be breathing into the computer that's actually measuring how much you inhale. Inhale, exhale, inhale, exhale. And then you get these values, and you'd be able to analyze the values. So we want to look at what it is that we want to look at. And this is always in volume and liters. So what's showing here, let me show you first, half a liter is about what you inhale and exhale in quiet breathing when you don't force it. You're just sitting there now watching, listening to me on the computer, and you have this inhalation and exhalation over time. It's about half a liter. So that value of half a liter is called tidal volume. And here, this individual, it's a tracing of someone who inhaled quietly, exhaled, no forcing, inhaled, exhaled. And then he was directed or she to take a very deep breath, maximum possible. And they inhaled and went up, 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 up to the max. And then out to the max. Out, 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 out. It's hard to get that much out. And then we're instructed to continue breathing normally, if you possibly know how to do that. So then you breathe in and out again. Okay? So these values then are important. Tidal volume then was the quiet breathing. Amount of air that moves in or out of the lungs with each respiratory cycle. We do this in the lab when we're in person and we hook you up to the computer. So let's see the other values described. The inspiratory reserve volume is the one in pink here. So is the additional amount of air that can be inhaled after a normal inhalation. So it's in pink here. Notice that it doesn't go from the bottom of a tidal volume to the top. It goes from the top of a tidal volume. In other words, this is what you would do normally. Now this is above and beyond the normal. And then you come back down again. So you get a measurement again in liters of your IRV, what your reserve volume is. In other words, if you needed to take a deep breath in, how much of that air can you inhale? IRV. Let's go now to expiratory reserve volume. And it's the amount of extra air above a normal breath exhaled during a forceful breathing out. So again, you're going to start here because this is what you would have exhaled normally. And you're going beyond that. You're breathing out and trying to get as much air out. So that's your reserve volume of expiratory. So how much you can get out beyond that. The value then that would include the tidal volume plus the inspiratory reserve plus the expiratory reserve would go from the bottom here all the way to the top. And that is a very important value. And that's called vital capacity. That is how much air you can actually move forcefully. So it's a capacity that your lung has to be able to move air. Notice that there's another little leftover here, and that's called residual volume, because when you exhale completely, your lungs don't totally collapse on you. There's still some air in there. It's very hard to measure. We don't use that measurement very much, but you need to know that there is a certain volume that will stay behind in the lung, and that's residual volume. So if you were to include that in your measurement, it would be your total lung capacity. But really, the value that we use more is this one. It's your vital capacity. It's the one capacity to move air. So defined here, vital capacity is the total air exhaled after forced inhalation, sorry. So you've taken in your maximum inhale, and then you go all the way through down to the maximum exhaled. And that is your vital capacity. When we do this in class, in person, we get very different values for different individuals in the class for the vital capacity. Total lung capacity then includes the residual volume. The total lung capacity in blue here, as I explained, is total, and it includes that residual volume there. But as I said, in medicine, it's more common to use the vital capacity. That's the value of air that you can move. Okay, we need to think of gas laws also. So we're going to take these one at a time. This is a table from your book. The first one says the total pressure of a mixture of gases is the sum of the pressures of the individual gases, and that's Dalton's law. So why are we talking about this, and why do we care? Because we're thinking of the total pressure of a mixture of gases that we inhale, and that is the sum of the pressures of nitrogen and oxygen and carbon dioxide, and then smaller percentages of other gases too, but we're going to stick to those. So the individual gases, 78% of that air that you're inhaling is nitrogen, about 21% oxygen, and 0.04 carbon dioxide. Okay, so the total pressure of all those gases together is the sum of the individual pressures of each gas. The second gas law is gases singly or in a mixture move from areas of high pressure to areas of lower pressure. So just think of a balloon. You're popping a balloon. Obviously, the air that's in this balloon is going to shoot out once that's open. So they will move from areas of a high pressure to low pressure, and that's important for when we breathe. And the last one is if the volume of a container of gas changes, the pressure of the gas will change in an inverse manner, and that's Boyle's law. I'll have to show you in a diagram. If you have a container, and this here is 1 liter, and you have 1, 2, 3, 4, 5 little molecules here of a gas, it has a certain amount of pressure, 100 millimeters of mercury of pressure inside this container, meaning these molecules are crashing along the edges of this container. Now, if I were to reduce the size of that container and make it only half the size, so now I only have half a liter of a container, what happens to the pressure in here of those same 5 molecules? I've got greater pressure because I've squeezed it essentially into a smaller container, and it's the same volume, but put into a smaller container. Therefore, the pressure in that container is going to be greater than the pressure in the larger container. Okay, so that's the relationship between pressure and volume. If you're keeping that volume and you're making the box smaller. I was referred to it as a box because we're going to make the analogy. This is a good analogy for what happens in your lung. You're changing the size of the box. You're changing the size of the lung. We're going to stop there and start the next one on the mechanics of breathing. Thanks.